Okay.
They're not freshmen, they're
Sophomores. We'll talk about them later. No, it's all right. The Hamiltonian operator. Okay, so we have this Hamiltonian operator. We looked at it for a 1D particle in a box, which is really one of the only systems that we can solve for exactly. But what do we care about in this class? Do we care about just individual electrons?
Well,
No. We care about all of them. We care about molecular systems. That might extend to periodic systems that could be just classified as one giant molecule, depending on how you look at it. But we're going to fall back to, again, our Schrodinger equation. Let's try to define a Hamiltonian for a molecule. You're going to need a whole page. For a molecule, let's think about the attractive and repulsive forces in a molecule. It's a question. And then what we're going to do when we think about those different subatomic particles interacting, or atomic particles interacting, we're going to construct a Hamiltonian. Okay. Energy. Energy is always made up of what two things? Or flavors, excuse me. Or types. Yep, kinetic. Potential. So we want to think about things in terms of kinetic energy and potential energy, but we can still think about those interactions. Okay, so what things are moving, what things are attracted in a molecule? Can anybody tell me anything? Let's make a list of attractive forces and then repulsive. And maybe attractive isn't the best word to use. Maybe energy lowering is better, but we'll go with it. It's all included in this. I want it in the most fundamental way to express it. So even simpler.
Electron and proton are attractive.
Okay, yep. And in this case, electron, and not just protons, because that would be like an H atom.
Okay.
I want to go beyond that.
Positive.
Yeah, nucleus. Positrons we're not going to worry about right now, but they're there. They're real. I've made them. Yeah, you can do these things where you make them in a gel. I had to do this for a lab. And you make a gel and you spiral them at one another. There's the electron, and then you have the positron, and they annihilate one another, and you get to see it. It's the most horrible experiment, not as bad as a Mulliken drop experiment. I worked on that one for like 3 weeks straight. That was horrible. No, I'd just be sitting there with a drop spray thing at like 4 in the morning, like squeezing a bottle and trying to get trap an oil drop. It was horrible. In my modern physics class, we were just left alone to the lab. So in physics, a lot of times it's like, figure it out. I'll see you later. Rather than in chemistry where you learn techniques and apply those techniques. So, but see, at least you have only one lab. I had every physics course had an accompanying lab. I actually was not a physics major because I refused to do anything more with optics. I blew up at that point. I hate optics. Anyways, back to what we're talking about. All right, what other attractive and repulsive forces do we got? E's to E's, electron, electron. Repulsive or attractive? Yeah. Electron, electron. What else? Nucleus to nucleus, yep. I didn't ask if it was repulsive or attractive. What is it?
Well, I guess you told us.
Yep, I did. Okay. So those are the attractive and repulsive forces. But we also have to, so these, what are all of these? What type of energy? Yeah, these are all potential energy. What about kinetic? Or what is kinetic energy? Movement. I'm not going to use heat. Heat is something else. Heat is the transfer of thermal energy, which is related to thermodynamics. Don't want to touch it. Kinetics, okay, what things are moving? Electrons are moving. And what else is moving? Yeah, the nuclei are moving. We need a term for every one of these things. What I'm going to do is I'm going to write out a Hamiltonian for a molecule, and then we're going to dissect what each of those terms mean. Okay? So give yourself literally a line across your page, because that's what you're going to need. The subscripts matter, so keep track of the subscripts. Okay? Each bar. If you can't tell what something is, please ask. But we will describe what most of these symbols mean. Oops. Already botched it. Whatever they're cooking at the Hickey smells so good. Yeah, I'm going to eat some Hickey food today.
Hey, do you want to experience the whirlwind that is our table again?
I'm eating right after this. I'm eating right after this. Wait, what is that upside down?
We'll get there in a minute.
Because analytical habits at the same time. I'll figure it out. It's all me.
I can teach anyone with Calc 2, I can teach anyone thermodynamics or quantum. I don't need. Calc 3 is very nice.
I have taken Calc 2. So.
Oh, yeah, you did.
Oh, yeah, I did.
Which one do you guys think is the most?
Calc 2.
Calc 1.
I had 3 different people for.
Calc
I
3.
had 4 different
Oh, I love
people for the
Calc 3.
4 calc.
Calc 3 was my jam, man. That's when I started liking calculus.
I agree.
Mhm.
Well,
Those are Z's. Okay, so now we got everything written out, hopefully. Capital. Where we're going to describe each one of the parameters, okay? M sub E. What do you think that is?
sorry, what's the I? Is that I
Is that
greater
the
than
mass of the
J?
electron?
I greater than J.
Love that.
Oh, I'm sorry, less than J.
Good enough for me.
Is that the mass of the electron?
That, yes, Joe is answering the question, I guess. That's the mass of the electron. Okay. M sub A.
Oh, yeah.
Mass of nucleus A. Whatever species nuclei we're talking about. Okay. R sub IA. What's that? Yeah. Or distance. Between electron sub I
Oh, I did it
and
backwards.
nucleus A. Okay, because we can have different number of electrons, different number of nuclei. What else are we missing? Z sub A. What's that? Yep, nuclear charge of A. Nuclear or
R.
R. There we go. EAR?
Yeah. Nuclear.
Yeah, there we go. Nuclear charge. Yeah, I know. Don't get me started on that one. I kept thinking about that on the play. I kept on trying to say it, and then I'm like hearing all these Dutch people being like, all right.
On the exam, I was gonna write
How do you say that?
Guten Morgen.
Guten Morgen.
Huh?
Guten Morgen.
Guten Morgen.
Guten Morgen. You don't say good morning.
Martin?
Guten Morgen.
I'd say Martin.
I don't know. And then like it was just a bunch of mixture of other languages. It was very interesting to hear people speak in English. And then when somebody was like, I don't know how to say the word, everybody just sort of laughed. Like there was a Spanish guy, and then like a Japanese guy walked up to give a talk. He's like, I have no idea how to say your name, dude. Here he is. Can you say your name for everybody? It was very funny. Way less angry than I feel like United States culture when it comes to differences. So that was refreshing. RIJ, what's that? Yep.
No, you got it. You got it.
Yep. Electron I and electron J. Then RAB is again another distance between what? Yep. Okay. Joe, you asked this question, and I don't think you're the only one who doesn't know. What does upside down delta squared mean? Anybody have an idea?
I can't remember what it's called.
Do you remember the mathematical? Okay, can you tell me what it means, mathematically? Partial.
It's like a partial of, you have like a partial of x,
Yep.
x squared, and a partial of y squared plus a partial of z squared.
Yep.
And then sometimes there's other
no.
stuff with like r's and
Yep. So when it's spherical polar coordinates, there's a bunch of r's and thetas and phi's, which I don't want to talk about. This is known as the gradient.
He did say that earlier.
Did I say gradient earlier?
No, he did my
Oh.
Before Katie basically called me stupid.
No. I just know that concrete is required to do that.
Before you erase that.
Yep. It'll be good. And if they're synergistic, it actually helps out a lot. Okay. What we're going to do now is we're going to look at each of these terms, and we're going to try to figure out what they mean. I'm going to erase this bottom part. You may want to rewrite them, or we can just box them with different colors. Am I okay to erase this bit here?
Yeah, I took a picture.
Okay. Get a bunch of colors. There we go. What I want you to pay attention to are the subscripts. Oh, shame on me. And the signs.
You're done.
Wait,
I know.
what do you,
I put a negative here. I should have put a negative.
That's what you gotta do to other people's
Yeah. All of the negatives, are they energy lowering or energy raising? Lowering, because they're negative. Does that mean it's favorable or unfavorable for the system? Favorable. Positive signs, unfavorable. Keep that in mind too. This first term, what particles or particle is it dealing with? Electrons. What is this? Given there's a second derivatives, Specifically, what type of energy? You got 2 guesses.
Potential.
Nope. Kinetic. This is kinetic energy of what? Yep, of electron I. And actually, we should say of the electrons is better. You're right, Lily, because we got that summation. Okay. Joe, if I put orange next to this, doesn't work, right? You want blue? Next to yellow?
Wait, that's not orange on the board.
That's yellow.
Oh.
So if you guys were that would
You do great.
Mm-hmm.
Yeah.
Now,
see, right,
this term, what is that one? Yep, of all the nuclei. Okay. We don't have anywhere to rush. White. There's a negative sign here that I just obliterated. What's this? What particles are in here?
This is going to be
Yeah?
the attractive forces of the electrons and the atoms.
Yep. So this is a potential energy, which is also an attractive force between nucleus and electrons. This term with the positive sign, the very first one, what's that?
Electron repulsion.
Yep, electron repulsion. And finally, this bit here. What's that?
Nuclei.
Yep.
It's all good. I butchered terminology.
Okay. So we have all of these terms here. Does this look simple to solve? Nope. There's a bunch of unknowns in here. There's a bunch of summations. What we're going to talk about next time is can we make simple assumptions to start whittling away at this so we can solve it? In reality, if we had a big enough computer, this wouldn't be impossible except for one term. What one term screws up everything? This term right here screws it all up. It's because of this we can't solve it directly because we have too many unknowns and not enough equations. And this has to deal with something called the many-bodied problem. So the current mathematics we have can't solve this exactly. We'll talk about the approximations we can make and eventually whittle down to molecules. We'll also talk about some other quantum aspects, and we might even talk about semi-empirical Hückel theory. Where we draw orbitals. Yeah, it's okay. Are there? Well, my question was: is there going to be any questions from anybody? So,
Is this kind of like what math is?
it's a lot of the fundamentals of what we just did. This is what you like touch at the very end of the semester. Okay, so you learn really about quantum mechanics and about what are operators and justifications for doing those things. And you start from the simplest model and work your way up to more and more complex models. So it's about the walking of getting to the complex models. In this class, we're jumping right to the complex models because we need to. We don't have enough time. It takes an entire semester to get to this point.
I can see it.
Yep.
I know I can see it. Only I can see it now.
Mm-hmm. Yep. What I want you to be able to do is look at this, and anytime you see mathematics associated with this, you should be able to be like, oh, that's a kinetic energy. That's a potential energy. Okay? And I want you to think about how are ways that you could approximate things to knock some of these out? What could you do? Okay? All right. Have a good day. We're going to spend a lot of time on this stuff for the remainder of the class, which is going to be fun, I think. And then we'll do some cool mathematics associated with stuff too. All right.